This video is about composite solids. It's found in your text in section 12-3. A composite solid is made out of two solids put together. In this case, we have a rectangular prism that's been put together. You can imagine them being glued together with this pyramid with a square base. So how would we find the volume of this composite solid? Well, let's name the parts of it. Let's call this part 1 and this part 2. And our calculation for volume is relatively simple here because the volume of the entire thing is going to be the volume of 1 plus the volume of 2. So the volume of 1 is going to be the base, the area of the base, times the height of this rectangular prism. Area of the base times, and we have to make sure that we're doing the height of the part of this solid that we're actually working with. So it's going to be the area of the base times 5. And then the volume of this pyramid is going to be, the formula for the volume of a pyramid is 1/3 times the area of the base times the height of the pyramid, which is 6. Now, am I going to get away with making the area of the base the same for both of these? Well, in this case, yes, because the area of the base of this pyramid is the same as the area of the base of this rectangular prism. The base is 4 by 4, so the area of that is 16. So I have 16 times 5 plus 1/3 times 16 times 6, which gives me a total of 16 times 5 plus 32, which gives me 112 cubic inches. Okay, now we're asked for the total surface area of this composite solid. This gets a little bit trickier because when we stick two shapes together, there's part of the surface area that actually disappears. The part that's glued together is no longer part of the surface of the solid. We can't see it. If we were to hold this in our hands, we would not be able to see this face that's in between the pyramid and the rectangular prism. So this we're going to have to be a little bit more careful with. We can still call these things 1 and 2. So the area is going to still be some combination of these two surface areas, but I'm going to invent a new kind of notation here. I'm going to say the area of 1 that's showing. So this little asterisk is going to mean the part that's showing, plus the area of 2, the part of that that's showing. So what part is showing for for shape 1? Well, we have a rectangular prism. We have its lateral area is pretty much like the normal lateral area. So we have the perimeter of the base times the height. That's the lateral area. But we only are adding on, instead of adding on 2 times the area of the base, we're only adding on 1 times the area of the base because this other base is hidden. So the perimeter of the base, if we take a walk around this base, that's going to be 16 units. The height of this prism is 5 inches. The area of the base is 4 times 4. That is a coincidence that in this case the area is the same as the perimeter. So we have 16 times 5 plus another 16, which gives us 92 square inches. Now, what about the part that's showing from this shape here? Well, the part that's showing from shape 2, we get a little break on this because the part that's showing is actually just the lateral area. The part that's showing is just the lateral area of this pyramid. We just get to forget about the base in this calculation. So that is a point in our favor here. So we do need, however, to find the slant height. We're not going to get away with not finding that. Here is the slant height, which is going to be part of the formula for our lateral area. So all we need is the lateral area, but that's going to be 1/2 times the slant height times the perimeter of the base. So our real trick here is going to be finding the slant height. In order to do that, let's imagine drawing this height inside of the pyramid, and then we're going to connect that center point to the edge here, and then the slant height is going to be here along the outside of the pyramid. Now, what is this height? Well, it's 6 because I'm just copying it from the height that's shown over here. What is the measure of this side of the triangle that I've drawn? Well, if we look down here and imagine dividing the base of this rectangular prism into 4 little squares, the center being here, we would see that this gets divided in half, and that this measure is simply 2. And then if we look up here, we can see that this measure is 2 because this is simply, we could do the same thing with the base of this pyramid. I didn't draw it up here because that would get kind of messy. So I'm going to come over here and draw this triangle flat. I have a height of 6 and a base of 2. This is obviously not drawn to scale. So the slant height then is the hypotenuse of this triangle that I've drawn. So I can use Pythagoras. 2 squared plus 6 squared equals the slant height squared. Careful not to make your S look like a 5 there. 2 squared is 4 plus 36, that's 40, is the slant height squared. So taking the square root of both sides, we have that the slant height is, in simplest radical form, 2 times the square root of 10. Okay, now we have the slant height, we can find the surface area of this thing here. So we have 1/2 times the slant height times the perimeter of the base. The perimeter of the base of this pyramid is the same as the perimeter of the base down here, which is going to be 16. So we have 1/2 times 2 times the square root of 10 times 16. Those 2's cancel, so we have 16 times the square root of 10 is, this is the lateral area, which is the same thing as the part that's showing of shape 2. So now we can add the whole thing up. To get the total surface area, then we have the part that's showing down here plus the part that's showing from up here. So we had, our numbers were 92 from part 1 plus 2 times the square root of 10 from part 2. And we're just going to leave it in that form because we have whole numbers, we have simplest radical form. There's no point in, we can't simplify that any further unless you wanted to get a decimal. And that will be in inches squared because we're talking about an area, not a volume. Okay, you try this one. Find the volume and total surface area of this composite solid. Okay, I'm going to do one more example for you, and this time I'm just going to sketch it out. I'm not going to get into the nitty-gritty of the numbers. I just want to show you a strategy for composite solid that instead of adding 2 shapes together, what we've done is we've drilled out a hole in the center of this shape. So what we're actually doing is we have a cylinder here, and then we're subtracting a cylinder, a smaller cylinder, from the inside of that. So you can imagine that the volume of this composite shape is going to be the volume of what it would have been without the hole in it minus the volume of the hole itself. Okay, so now we have 2 cylinders. We can deal with that. We have volume 1 minus volume 2. The volume of a cylinder is pi r squared times the height. So this will be R1, and then we have minus pi r squared times the height. That'll be r2. The height, we don't have to label 1 and 2 because the height of both cylinders is the same. So this is a strategy for finding the volume of this composite solid. I'm not going to put in the numbers. I'm going to move on to showing you how to find the total surface area of this composite solid. Now that gets really interesting because would it be true to say that the total surface area is the area of 1 plus the area of 2? Or would it be true to say that it's the area of 1 minus the area of 2? Which one is it here? Because we've taken something out of this shape. Take a second to think about that. Okay, in this case, we're going to be adding the areas because even though we have subtracted or taken out part of this solid, we can actually see more area now than we could before because we can look down into this hole and see more surface area than we could have if that wasn't drilled away. So we're going to be adding the part that's showing from shape 1 to the part that's showing from shape 2. That was the big insight that we needed for this problem. But there's another complication here, which is that the part that's showing here on the top and the bottom is shaped like a donut, and we've never calculated the area of one of those before. So let's start with the big cylinder, the part that's showing. We have the lateral area, which we are now experienced at finding. That's pi times the diameter times the height, plus this funny shaped donut. And we have two of those. We have one on the top and one on the bottom. So let's just focus on finding the donut shape. Well, what we really have here is a circle with a little circle taken out of it. So we have pi r squared, the big one, minus pi r squared, the little one. So if we were to take that and multiply it by 2, we would get the area of these two bases. And then we could add it on to this same old pi times the diameter times the height, and we would get the area that's showing from this big cylinder. Then we could easily calculate the part that's showing from the small cylinder because that's just the lateral area. The whole just is the sides of itself. It doesn't have a top or bottom. So we got away with something there without having to do a lot of calculation. We can just say pi times the diameter, the little diameter now, times the height of that whole thing. So this would be a strategy for setting up this kind of a surface area problem. You try this one. Find the volume and total surface area of this composite solid. For further practice, see page 494, numbers 29 and 33.